Welcome to today's lecture, in which we are concerned with the finiteness theorem for semialgebraic sets. You have already heard about the finiteness theorem for semialgebraic classes, which we treated in section 5.4. But today we are speaking about a quite different theorem for semialgebraic sets. Which, however, has in common with a previous theorem that the statement says that something is a finite union of things of a certain form. Okay, so let's go into this. And it will actually build up on the Boyer-Sewicz inequality, which we have learned about last time. Okay, so let n be a non-negative integer and a subset S of R to be n. So R, remember, was of course a real closed field. So in this chapter, R was a real closed field and K was a subfield of R. And curly Sn denoted the Boolean algebra of all K semialgebraic subsets of R to be n. Okay, let n be a non-negative integer and S a subset of R to be n. And such a subset is called K basic open if it can be written in the following way, namely as the set of solutions of a finite system of polynomial inequalities, namely, and in fact, strict polynomial inequalities where the polynomials have coefficients over k. Okay, so note that such a so what does motivate this? Why do we call this K basic open? This is because it will turn out later that these sets are in some sense building blocks for arbitrary K semialgebraic open subsets of R to n. The same thing for K basic closed. So in that case you take here non-strict polynomial inequalities and everything else is the same, right? So first observation, every K basic open subset of R to n is K semialgebraic, of course, and open in R to n. Why open? Well, because such a set S here can be written as a finite intersection of open sets. These sets are of course open, right? That we have seen, for example, in 6.1.12b. Okay. Where we have seen that such sets, when P ranges over all polynomials with coefficients from R, actually generate even the topology. Here the coefficients are from K, but okay, this is not a problem, of course. That's even better. Okay, so and when you have that, we have also that every K basic closed subset of R to n is K semialgebraic and closed. Okay, so now the finiteness theorem for semialgebraic sets says the following. So let n be a non-negative integer and S a K semialgebraic subset of R to n. That is, in the first case, open, when we claim that S is a finite union of k basic open subsets of R to Vn, right? So we can write it as a finite union of k basic open subsets of R to Vn, right? Of course, for k basic open subsets, in the way they are written, it's completely obvious that they are open. And then every union, in fact, of them would also be obviously open. Here you even take just a finite union. And we have the second version of the theorem is about closed k semialgebraic subsets. So if you have such a closed k basic semialgebraic subset, when it is a finite union of k basic closed subsets of R to Vn. And since finite unions of closed sets are closed in any topological space, this again means that you can write it in particular in a way that makes obvious that it is a closed semialgebraic subset. Good. So in fact it suffices to prove one version of a theorem because they are both equivalent. The green version here is in fact equivalent to the yellow one, because S is a finite union of k basic open subsets of R to Vn. If and only if S is a finite union of finite intersections of sets of this form, of course, right, where G is a polynomial over K. That is by definition of k basic open. And that means what does that mean for the complement of S? For the complement of S, this means that it is a finite intersection instead of union, right? Of finite unions instead of intersections of sets of a form. And now I have to write here less than or equal 0. But since G is an arbitrary polynomial over K, I can also take minus G instead of G. Minus G is in fact also when an arbitrary polynomial over K, and instead of writing G of x less than or equal 0, I write G of x. I could write minus G of x greater than or equal 0, and if I exchange minus J with G, then I can write this. And then I can write this is equivalent to a complement of S being a finite a finite intersection of a finite union is by 181 of sets of a certain form is by 181 a finite union of finite intersections of such sets, and vice versa. Let's look at 181 again. That was this important trick. Here, finite. So let's see, what did we have here? We were concerned with a finite intersection of finite unions and finite unions of finite intersections. Yes. Okay. Here, if, for example, here I can write any finite union of finite intersections as a finite intersection of a finite union of finite unions of the same sort of sets, right? And also vice versa, right? You only have to, if I and Ji's are finite here, then this Cartesian product of Ji is also finite, right? And I is finite. Okay, so that works with the additional condition that these are finite unions and finite intersections. Okay. And then this means that the complement of S is a finite union of k basic closed subsets of R to Vn, right? And by the definition of k basic closed. And yeah, and so you know, the first version of a theorem, the green version of a theorem, is yeah, so I mean, if I prove the green version of a theorem for all S, when I prove when this is equivalent, so the green version of a theorem for all S is equivalent to the yellow version for all complements of S. but every semialgebraic set can be written as a complement of a semialgebraic set, of course, namely it's a complement of itself. And yeah, so so it suffices to prove one of the versions, so we show the open version. Okay. Good. So we write S like we can write every k-semialgebraic set, right, as a finite union of sets of this form. So this was 611. That was just this does not use that. This does not yet use openness, actually, right? It uses just that our set is k-semialgebraic. And now, the idea is that okay, so we fix one of these sets that contribute to this union here, and we find a k-basic open set U, which contains this set, and at the same time is contained in this open set S. Okay, so if I look at this at this containment here, when I take a finite union here everywhere, so if I have for each I with these two inclusions here, right, then I can take the union. When I can take the union here from 1 to k, and yeah, I fixed here I, right, so I don't have to write ui because I is anyway already fixed, but if I wrote here ui, then I could take a union of these ui's, and here I take just S. But S equals this thing here, right? So these two inclusions must be equalities then. And so I get that S is equal to the union of these ui's. So it's a finite union of k-basic open sets as desired. Okay, but now the I is fixed, and I want to squeeze in this k-basic open set U here, right? And yes, so the basic idea of how to squeeze in a basic open set here is as follows. Maybe I draw a picture. Okay, so the dashed line should delimit my set, but should not belong to a set. Okay, and yes, and so this is so that's so okay. So maybe let me fill it. So you know that should be my set S. I mean all that. Okay. That should be my set S, more or less. Okay, and when I have here, so this should be a finite union of such sets here, right? So yeah, I don't know exactly. Maybe you have here 3 parts. Maybe that's 1 part. Maybe that's S2, right? And maybe that's here S1. And maybe that's S3. Okay, so actually for S2, I have to correct myself a little bit. The 2 endpoints here should not be in it. Okay, so let me symbolize it like this. And so that's it more or less, right? Okay, so S equals so S equals S1 union S2 union S3. So maybe this is not an ideal example because it looks like if this were a union of pairwise disjoint sets. So if it were a disjoint union here, that would be a little bit a special case, but okay, anyway, I think that's good enough as an example. And now consider the complement A, right? So A is the complement. So A is the complement of S. And the idea is that this U, which I want to squeeze in here, arises by relaxing a little bit this equation here. So namely, you could say instead of taking here fi of x equals 0, you take something like, let's try, for example, with minus epsilon smaller fi of x smaller than epsilon. So epsilon lies close to, fi of x lies close to 0 instead of being 0. Okay, I don't yet specify what epsilon should be, and in fact it will not work that easily. By the way, I should say that you could in fact write this as one single equation by saying fi of x squared is smaller than epsilon squared. But that will perhaps not work. You know, for example, it could happen that that this fi here comes very close to 0 when you go out to infinity somewhere, right? So, I mean, yeah. So, for example, you know, maybe let me give you an example of a polynomial that becomes very small when you go to infinity. So let me give you the following. Let's just take the real numbers for simplicity. So I have two variables x and y, and I take a polynomial in these 2 variables, namely x, namely. Let me think. So xy minus 1 squared plus x. So this polynomial, in fact, it's real zero set. So you know, if you are so this is okay, maybe I write x squared in fact here. Okay, so this polynomial p, this real polynomial p, is non-negative on R2 with 2. Okay, because it's actually a sum of squares, right? But if you look at it on the hyperbola defined by x times y equals 1, x times y equals 1, right? So that's this curve here, this green curve. And now if you move, for example, on this branch of a hyperbola, and you move towards, let's see, so you move in this direction here, right? So you go out to infinity here, right? When on the hyperbola, this polynomial agrees, the values of this polynomial agree with the value of x squared, right? The x coordinate, of course, goes to 0 when I move more and more outside on this branch of this hyperbola. So here it goes actually to 0, right? So it takes arbitrarily small values on the plane, but in fact it never gets 0. In order to get 0, you would have to be on the hyperbola, but on the hyperbola it's actually nowhere 0, because you know the x coordinate is never 0 on the hyperbola. Okay, so so you see, so polynomials can take very, very small values when you go out to infinity, and so the example of such a polynomial I just showed you, of course, was one which was positive on R2 with 2, but note that okay, that probably then can also happen for other polynomials which vanish somewhere on the plane, right? So in particular, let's look at this set S2. You could easily imagine that this is defined by some, it looks like it is defined by some, by using really some polynomial inequality fi of x equals 0, which is not a trivial one, right? And whenever I relax, when from fi of x equals 0, I go to fi squared of x is smaller than epsilon, let's say, and epsilon is now positive. I don't write epsilon squared, I just write epsilon now. When I do such a relaxation, then it could perhaps at least happen that suddenly something pops up here which I don't really want, right? Some far outside, right? Okay, so that you could perhaps avoid, you know, by dividing here with something like, let me see, so instead of epsilon you write maybe epsilon over 1 plus some xi squared, or xj squared maybe, because I is already taken, to some k, right? So the idea is a bit that you make the epsilon, maybe we call this epsilon of x. So you adapt the epsilon. When x is far outside, you make it even smaller. When x is very far from the origin, you make it even smaller, right? That could perhaps solve this problem. You can easily imagine that there can be other problems, not only this problem at infinity, right? If you are very close here to this point, right? Now, if you relax a little bit, like so, if you relax this equation a bit, you just say if I is close to 0, then you can easily imagine that you can, I mean, you can perhaps afford to relax quite a lot, right? But here, when you come close here to where set S comes to an end in some sense, then we have to be careful perhaps, right? Because we really have to make sure that nothing here is added, right? So this would be not a good idea here, right? So we have to make sure that we should be more careful here. So maybe we should be more careful. Sorry. So that was unintended. So okay. So maybe we should be more careful where we GIs, where we G or some GIJ, let's say some one of these GIJs from here is not only for this fixed I maybe, but for all of them is small, right? And so the idea in the end is that here you add something like product from J equal 1 to M Gij. Actually, it's for the fixed I. That should be good, right? For the fixed I, one of the Gij's, none of the Gij. If one of the Gij's is small, so let's say if for example the product here is small, product of the Gij's for this fixed I, if this is small, then maybe you have to take a little bit more care, right? So maybe this should also go into our epsilon of x. So if one of the Gij's gets very small for our fixed I, then maybe let's be more careful. Let's relax a little bit less, right? So in the end, we will relax such an equation to something like, if we rewrite this here to something like 1 plus some j equal 1 to n xj squared to the k times fi squared of x less than epsilon times this product. So that's very roughly the idea. And so we would have to make sure that so we have to make sure that such a thing does not add anything outside of S. That means on A, such a thing does not is never fulfilled, let's say, where the Gij's are positive, okay? Okay, for our fixed I, right? So that's a bit the idea. It's not very easy to explain though. So that's why we look at this function f on A, fx maps to fi of x squared, and we look also at this function. Now, why this function? Because on A, if this function is 0, right, at a point in A, so if f of x is 0 for an x in A, then I know that one of the Gij's must be 0 or smaller than 0, right? because this set here is contained in S, right? So and Vi is fixed, as I said. Okay, so and then this absolute value plus this thing here is 0, right? And so this product is when 0. So I know that if f is 0, then g is 0. So that's just a trick to get the hypothesis from our variant of Woyer-Savage inequality, right? So we have for all x in A, f of x equals 0 implies g of x equals 0. By 624, that was our variant of Woyer-Savage inequality, which holds for all closed sets, right? We need continuous case semialgebraic functions that we do have, as you see easily. When we get this thing here, right? So we get such a constant, and we get okay. Let's see. So we get this constant here in the non-negative elements from K, such that for all x in A, the absolute value of g of x to n is less than or equal c times 1 plus the norm of x squared to a k f of x. Right, 624. Let's look at it again. Exactly. So that's that's exactly what we have there. Okay, so for all x in A, as I said, so using this absolute value here was a trick to be able to apply Woyer-Savage inequality on this closed set A. For all x in A satisfying that the GIJs for our fixed I are all positive at x, we have that this becomes then, of course, 2 times this factor here becomes 2 times Gij of x. So if I factor out the 2, when I get 2 to the m, this product to the n is less than or equal to a constant capital C times 1 plus sum of the xj squared to the k. And here I just take a definition of f of x, fi of x squared. Right, so we have, now if you compare this to what was the idea a little bit, is that so we are almost we have almost the thing we wanted, because so we have to make sure that this does not hold outside of S, right? That this does not hold outside of S, and if you put the C, which you should think of being potentially very, very big, to the other side, when we have here, 2 to the m to the n divided by C. Well, you should think of C to be very big, but that looks also very big, 2 to the m to the n. So, well, but in the worst case, so you don't really know if this quotient should be, you should think of it being big or positive or small and positive, but in the worst case, it's small and positive, of course. It's very small, so maybe you could think of it like with epsilon. And you see here that epsilon times this product here, epsilon times this product is actually here less than or equal, so it's the contrary of being bigger than this thing, right? So it's really a negation of this somehow outside of S, the negation of this holds, right? So that means if you relax, if you take this relaxation of this inequality, then if you take this relaxation of this equation, then you don't add anything outside of S, right? There is nothing like, such a thing, which in addition to these things here is added. Okay, so yeah, it's a bit a surprising application of Weyer-Savage inequality, but once you think about it, it's not so surprising anymore. And set U to be now we write in fact, with negation of this here we add this, instead of fi of x equals 0, we add this thing here we replace the fi equals 0 here by this strict polynomial inequality. That's, by the way, a polynomial inequality over K. So this is a K semialgebraic set, basic open one, and U intersected A is now the empty set, of course, and this is certainly contained in U, and U is contained in S because its intersection with A is empty. Okay, and we are done. Okay, so we thus have proved, in fact, the finiteness theorem for semialgebraic sets. And maybe let's now look at an example which illustrates this a little bit. Okay, so a slash square is our example. So I take here a semialgebraic subset of R2. R can even be a real closed field. And I take such a square here. And the dashed line means delimits the square and means that that only what is inside this actually belongs to a square. Okay, so it looks like this. Okay, and so it's just the open interval between -1 and 1 to a square, right? And I take away something from it. I take away from it 0, 1 cross 0. So that's actually this set here. Okay. So this point was anyway not in a blue set, so I cannot take it away, but okay, so I write it in that way in order to make clear that this red thing here is closed, right? That's certainly the case, and this is open, certainly, right? In the topology that we have on R2, which is a product topology of the order topology. Okay. Okay, so let me take, okay, let's define this set S. And how does S now look like? Well, looks like this, right? So S looks like, let me see, so S looks like this. So we have this slash here, and it's open, and it's certainly semialgebraic. Okay, so we know by it's actually Q semialgebraic. So we know by the finiteness theorem for semialgebraic sets that it is a finite union of K basic open subsets of R2, right? K was a subfield of R, it could be Q even. And yeah, indeed it is. So how can you do this? We could of course try to follow a proof of a finiteness theorem for semialgebraic sets, but maybe let's just do it like this. So I can, of course, yeah, it is not surprising that I write down this inequality for the x-coordinate, right, which is valid on S. And then I write somehow that y coordinate lies so okay, I write down a univariate polynomial in so maybe let me think of it like this. So if you 0, 1, -1, and now look at the polynomial which does the following, which is positive strictly between -1 and 0, and again positive strictly between 0 and 1, and otherwise less than or equal 0, right? And such a polynomial is of course y plus 1 times y squared, or if I evaluate it in y, when it's y plus 1, y squared times y minus 1. That does maybe minus this thing actually, yes. Okay, minus this thing does certainly the job, right? So that's what I wrote here. And that, of course, defines now, that would define now a thing which is a little bit different still, because it has also a slash here. It has a second slash here. So it has actually a slash everywhere here. And now I have to, I take the union. I take the union with something like, which adds the other slash, and I can do this actually. In this case, I can do it by taking here a disk around that point, around the point -1/2, 0 of radius 1/2, right? So by adding this disk here, I add in fact again this part here of this red line. So I add actually this again. Okay, so here I did it just by hand somehow, right? So, but that's an example. So here I have written this as a finite union of basic open sets. K basic open sets. Okay, so that's what is written here. So it's a union of two K basic open sets. However, S is not k-basic open. So that's because you could maybe think maybe every open k-semialgebraic set is actually a basic k-open set, but that's not the case. And why is this not the case? So to show this, we assume it is. So we can write it in this way. When these GIs, since they are yes, GI of x 0 has to be non-negative for all x in 0, 1, right? So that means the GIs have to be non-negative on this red slash here, because they are actually non-negative close. So if you have a point on this slash here, then very close here, right, there is a point where the GI is even positive, right? Either here or here, right? For this thing here, also you have to go a little inside. So that's a very easy continuity argument. And then, but this red thing here does not intersect S, and thus we have that this interval here is the union. Because so what is written here? So on every point of this red slash here, in every point of this red slash, it must actually be true that one of the GIs is 0. Not only is it's anyway greater than or equal 0. We have seen it here, but not all of them can be positive, because otherwise the corresponding red point here would be in S, right? So at least one of them has to be 0. So for every point here, there must be an I such that GI of x, for every x here, there must be an I such that GI of x0 is 0. So, this is certainly an infinite set. So there must be one index I for which there are infinitely many x's in this unit interval, such that GI of x0 is 0. But without loss of generality, after renumbering the GIs, I could say that this is G1. Okay, so I have that the number of x in the unit interval such that G1 of x0 is 0 is infinity, so there are infinitely many. But then the univariate polynomial G1 of capital X is a variable, G1 of capital X0 is 0, this univariate polynomial is 0. And consequently, if I look now on the x-axis, on the first axis here, that does not intersect S at all, right? So this part of a slash, this part here could also not belong to S then, right? But that does belong to S. Okay? So here you see not every open k-semialgebraic set is k-basic open, but it's always a finite union of k-basic opens by the finiteness theorem for semialgebraic sets. So now we learn about an abstract version of the finiteness theorem for semialgebraic sets. So here we suppose that R over K is algebraic. I mean, that was not at the beginning of this chapter, at the beginning of chapter 6, where we are now. We just said that R is a real closed field and K a subfield of R, right? But here we, in addition, we suppose that R is algebraic over K. Yeah, but then of course R is the real closure of K together with the induced order, the order that R induces on K. Now let n be a non-negative integer and write A for a polynomial ring in n variables over K, and let t be again the preorder generated by the non-negative elements in A. When we are in the setting described before 363, so let's go back, 363, 363, okay, so that was this setting here. So an ordered field K less than or equal, R its real closure, n in n0, A is this, T is this. So yeah, so we are exactly in this setting, right? And we had here, and denote by the fattening again, with fattening of K semialgebraic sets, so that fattening of a K semialgebraic set is a constructible subset of a real spectrum of the preordered ring AT. And confer, for example, 364,531. 364,531. So 531 was this thing here, right? Fattening. So we had here, we had here a slimming. You remember this, and the converse was for fattening, and they were both isomorphisms of Boolean algebras which were inverse to each other. And for example, if S is such a K semi-algebraic subset of R to the n, when the fattening of S is the closure of these of a set of prime cones corresponding to points in S in the real spectrum of IT. With respect to the constructible topology. And so that was one description of fattening, and the other one, 364, is the older one, which is a bit more easy to understand. So that was just that it's the inverse of a slimming, and the fattening, for example, of fattening of such a set is actually this set, right? Here you could also write f hat of P is non-negative. So I hope you, so you could also write like this, this is the fattening of this. So I hope you remember all these things. If not, go back and look at it again. Now there are two statements here. So S is, the first one is that S is open in R to n, if and only if fattening of S is open in the real spectrum of IT. So S is a K semi-algebraic subset of R to n. We fix one, and when we claim that S is open in R to n, if and only if its fattening is open in the real spectrum of this preordered ring, right? And when the other statement is S is closed in R to n, if and only if a fattening of S is closed in the real spectrum of AT. Of course, this is, if I don't say anything, it's with respect to the usual topology on the real spectrum of AT, that's the spectral topology. And since the fattening of S is actually a closure with respect to a constructible topology, it wouldn't make sense. It wouldn't make a lot of sense, because when it wouldn't make a lot of sense to have this here with respect to a constructible topology, because the fattening of S is always closed, of course, since it is a closure with respect to a constructible topology. Okay, so yes, so of course it suffices to prove one of these statements, because for all S in Sn we have S open in Rn if and only if a fattening of S is open in the real spectrum of AT. That is equivalent, of course, to another version of this, namely, if S runs over all k semialgebraic subsets of R2n, then the complement of S also runs over all them. So I could I don't change anything if the truth value of this statement doesn't change if I put here everywhere the complement. So a complement of S, right? But the fattening of a complement, that's of course the complement of a fattening, because it's a homomorphism of Boolean algebras, actually even an isomorphism. And then the complement being open means the original set being closed, right? So I can now, let me do this maybe with black. So I can delete this and can say here closed. And here also I delete this and say here closed, right? And so I get the other version, right? And in the same way I get, of course, back from the yellow version to a green version. So let's concentrate on the green version of a statement. And here I would like to, we should first find out what is the easy direction and what is the hard direction. And at least in the case k equals r, which is kind of a special case, it seems that we know what is the easy direction and what is the hard direction. So let's perhaps first look at that case. So k equal r. So namely, in this case, this is easy. Suppose fattening of S is open in the real spectrum of AT. Then I know that, let's maybe go back to 6.1.12c. So here, so what I'd like to remind you of this here. Viewing R to the n, so in yes, so viewing R to the n in virtue of this injective map here as a subset of a real spectrum of a polynomial ring over R in n variables. Namely, the map is X maps to this prime comb Px, which consists of all polynomials which are non-negative at X. The topology on R to n is induced by the spectral topology, right? So yes, so I identify R to the n with a subset of a real spectrum via this injective map, right? And and the topology when is really the induced topology, right? So here I have, in some sense, I have S equals the fattening of S intersected R to the n, right? So here this I have this identification. Maybe if I want to write it without this identification, then I would have to write S is a set of all x in R to the n, such that Px is in a fattening of S. And yes, and since we since R to the n carries the subspace topology, right? It's an intersection of this open set with R to the n. Yeah, that's exactly by the definition of a subspace topology. That is when open in R to the n, right? So S is open in R to the n, and that's it, right? Okay. So why can't we do this if k is not equal? So in this case, it seems really that at least by what we have done before, that this direction is really easy. Now, if k is not equal to r, if this is not equal to r, it is not that easy, right? Because we don't know yet actually that that the same thing is true. That again, so actually the analog of 6,1. So the analog of this is actually true because R over K is algebraic. Turns out that it's still true that the topology on R to the n is induced by the spectral topology on the, and now here I have a preordered ring AT where A was K x1 up to xn, and T was the preorder generated by the non-negative elements from K. So that will still be true because R over K is algebraic. And that we will learn, and then I can do exactly the same argument, of course. And that we will learn only later here in this remarks 638. And yeah, and so we will have to, and that's actually because R over K is algebraic. Here that's in the situation of 635. So it's important here, we will use that R over K is algebraic, right? Okay. Okay, now I said it's, in the case K is not equal to R, it's not that easy. Well, it's actually also quite easy. I mean, currently in the lecture notes, it doesn't seem so easy. Let's take a little look. Currently in the lecture notes, the general case doesn't seem so easy, but I realized that it's actually much easier than that, right? So I have to change this in the lecture notes. So here I actually use some things. We don't even have to read it, right? But I use that the fattening of S is quasi-compact with respect to the constructible topology, etc., etc. So this proof is way too complicated, actually. So please just forget about it and let me do another proof. So direction from right to left. Let fattening of S be open in the real spectrum of IT. when by definition of a spectral topology, so I can at least reuse a part of this proof. So by definition of a spectral topology, the fattening of S is a union of sets of this form, right? Okay, and now what I did here in this proof is way too complicated. I wanted somehow to argue that it is a finite union of such sets. And this I could do because I know already that the fattening of S is quasi-compact with respect to constructible topology. Okay. And that argument I just don't need here, right? I wanted to use this argument because, you know, when I can write the fattening of S as a finite such union, yes, and when I can just apply the slimming on both sides. So when I can apply here the slimming, so, and when I wanted to apply that the slimming of a finite union is a finite union of the slimmings, because slimming is a homomorphism of Boolean algebras. But this actually is true also for infinite unions, right? You have to be careful. A homomorphism of Boolean algebras doesn't have to be compatible with infinite unions, but and the fattening, for example, isn't, right? But the fattening isn't, but the slimming is. The slimming is, right? The slimming is just by its very definition. The slimming is by its very definition is compatible with arbitrary unions. Okay, so let us look at the definition of a slimming, which is here. Okay, so the slimming takes a constructible subset of real spectrum of AT. We are still in the same, exactly the same setup here, right? And maps it to a set of all x in R2n. So it takes such a constructible subset of a real spectrum of IT and maps it to a set of all x in R2n such that px lies in C. Now the slimming of so now if you take here, so we could have defined the slimming on arbitrary subsets of real spectrum of AT, not just constructible ones. We could have defined it exactly in the same way, but I wanted it to be an isomorphism of Boolean algebras. That's why I defined it only on that Boolean algebra of constructible subsets. Okay. Since I defined it only on this Boolean algebra, so I have, if I say it respects infinite unions, I should of course take an infinite union of constructible subsets, which is, and this is an extra condition, again a constructible subset, just so that it's defined, right? So if, so I could say here if Ci in I is a family of constructible subsets of a real spectrum of AT, such that, just that, so that the slimming is defined, such that the union is constructible, you know, and if I had defined the slimming on all subsets of a real spectrum of AT, I wouldn't need this extra condition, but here I need it just for technical reasons, such that this is constructible when the slimming of a union of VCIs is the union of the slimmings. Yes, and I think you see it, right? You know, because let me just argue like this. So if you have here the union of the CIs, when this is of course the union of a set of the sets X in R to N such that Px lies in Ci, right? That's for freshmen, university freshmen, learn such or prove such things in their first weeks at the university. Okay, good. So yeah, that actually helps here a lot. Okay, so let the fattening of S be open in the real spectrum of AT. When I can write it, like yeah, maybe I now write down a new and easier proof here. So this I can. I don't need this anymore with complicated arguments. So I don't need here finite union. It's a union of sets of a described form. Okay, that is, S is, on the other hand, here I need now an index set which could possibly be infinite. So I in I, union over I in I of so let me make it again like this. So the fattening of S is the union overall I in I in I of such sets here. And actually maybe I have to take here an MI. I cannot maybe take a priori, I cannot take the same M for all I in I. Okay, so okay, with okay, so with MI in non-negative integers for each I and each Gij in A. Okay, it follows. Here I wrote by 364. That was probably that with slimming is homomorphism of Boolean algebras. Yes. So yeah, that it is an isomorphism of Boolean algebras, for example, right? So it follows here. Here I should now write something a little bit different. Maybe I will do it. I will figure out what I write in the end in the lecture notes. But for now, let me just write by the very definition of slim. It follows that S is when is union over I in I of all X in R to the N such that this is okay. So yeah, so that's that's just applying slimming on both sides, right? So I apply the slimming here, and I apply it on the right hand side here. But as I said, that means since it's compatible with this union, that means I can apply it here, right? And then yeah, when I use that, it's also compatible with finite intersections, right? And when I use its definition also. Okay, good. in particular, S is open. Yes, because it's a union of open sets. Okay. And yes, so if a fattening of S is open, then S is open. Okay, and here you see actually already I used just polynomials with coefficients from k, right? And if I had also the other direction of a theorem already proved, namely that S open implies fattening of S open, when I can go back here and I see that each open set actually can be written like this, even with polynomials who have coefficients in k. That works because R over k is algebraic. And we will see this later here when we say the topology is generated by these sets where P ranges over polynomials with coefficients from k. Okay? Good. So you can already note that. Okay. So now for the other direction, that's actually the okay, maybe I should say that this should be corrected in the lecture notes, this whole thing here. Okay, then for the other direction, it looks quite short, but it's actually the hard direction because I use here the finiteness theorem for semialgebraic sets, which is non-trivial, right? Okay, so by the because it uses that, in fact, it uses again Weyer-Sevich inequality and so on. So by the finiteness theorem for semialgebraic sets, we can find Km in N0 and Gij in A such that star holds. That's now, here I have a new form of star where I have an infinite union, but originally it was a finite union over K sets, right? And Vm I could choose the same, that doesn't matter too much. So here I have a union from I equal 1 to k, and here I can, if I want, I can take the same m all the time. So that's the other version of star. Yes, because you remember the finiteness theorem for semialgebraic sets was this thing here. And k basic open set was a set of this form. And it says here it's a finite union, right? Okay. Okay, so it follows that when double star also holds, and of course this was the original version of double star is meant here, where the union is from I equal 1 to k, and if I want I can take the same m. Right? That's just because the fattening is a homomorphism of Boolean algebras. It's compatible with finite unions, right? Please do an exercise that it is not always compatible with infinite unions. You should be able to do this. Okay, so yeah. Okay, so yes, and then a fattening of S is open because it's a union of open sets with respect to a spectral topology, of course. Actually, a finite union, okay, but arbitrary union would also be okay. Good. So it's a bit subtle. So maybe what you could not yet understand is why I say this is an abstract version of a finiteness theorem for semialgebraic sets. Certainly we used, for the difficult direction, we used certainly the finiteness theorem for semialgebraic sets. But why is it actually an abstract version? Okay, so first of all, it looks strange because here we have restricted to R over K being algebraic. In fact, otherwise we don't even have defined the fattening and the slimming. Okay, so maybe let's copy it here. So the description of 635 as an abstract version of 633 is motivated by the fact that one can easily retrieve a letter from a first. Okay, I mean, any two true mathematical statements are equivalent, right? True is equivalent to true. So, but what I mean here is it's easily derivable one from the other, right? So you have seen that the hard direction was very easily could be derived very easily from a finiteness theorem for semialgebraic sets. I mean the hard direction of his theorem, of his abstract version. And but also vice versa, if you know already that version, then you can deduce the finiteness theorem for semialgebraic sets from it easily. Even though here I have assumed R over K to be algebraic, but that is actually without loss of generality. Note namely that first one can reduce in the finiteness theorem to a case where R over K is algebraic by using the transfer of K semi-algebraic sets between R and real closure of K with the order induced by R. So yes, you know, so it's actually easy to see that the thing is as follows. So you have here K, and here you have together with some order, it's actually the one induced by R. So you have here an extension of ordered fields, and when you have so these are two extensions of ordered fields here. And now I have a K semi-algebraic subset S in R to the n. So it lives here somehow. I mean, it lives in R to the n. And now I can, and it's open, right? Now I can transfer it here, right? So I can interpret it. So if I call this R prime, I can, it's transfer from R to R prime makes this into a K semi-algebraic subset of R prime. Okay, and if S is open in R to the n, S open in R to the n implies that this transfer is open in R prime to the n. So maybe let's think about that later. This transfer preserves openness, okay, and also closeness, right? And yes, so and then I could apply if I know already the finiteness theorem for semi-algebraic sets in the special case where R over K is algebraic, when I could now say that, okay, this is a finite union of K basic open subsets of R prime to the n, and such a finite union of K basic open subsets of R prime to the n with if I do a reverse transfer from R prime to R, transfers it, of course, into union of K basic open subsets of R to Vn, right? The transfer of a k-basic open subset of R prime to Vn would then be k-basic open subset of R to Vn. So that's easy. So the only thing is that the transfer preserves openness. Maybe let's think about that in a minute. So, okay. And in this case, we can anyway reduce to this case that R over K is algebraic. So for this one has to argue that this transfer preserves openness, which can be accomplished by real quantifier elimination. Okay. So let's now, and that has nothing to do with R over K algebraic. So we can actually do this. So let's again have here an ordered field and two real closed ordered extension fields R and R prime. And now I have an S contained in R to Vn open. Now I claim that the transfer from R to R prime of S is again open. And how do we do this? We look at the classification of one way of doing it is we look at the classification from R of S, right? This is a K less than or equal semi-algebraic class, right? And now it's easy to see that the set of all it's an easy exercise to show that the set of all R in curly R, in curly R are, if you want, a class of all real closed extension fields of real closed ordered extension fields of this fixed ordered field K less than or equal. Maybe I should use here R double prime because the R and R prime are already taken here. So the set of all, the class of all real closed extension fields, real closed ordered extension fields of K less than or equal R prime prime, such that the classification, such that certification to R prime prime of this classification is open. That's actually again, so that was actually an n-ary K less than or equal semi-algebraic class, and this is a zero-ary K less than or equal semi-algebraic class. Why? Because this is actually the set of all R prime prime in R, such that there are different ways of doing it, but I could say like for all x in R prime prime to n, there exists an epsilon in R prime prime, such that epsilon is bigger than 0, and such that for all y in R prime prime to n, if the norm of y is less than or equal epsilon, if you want, take norm squared, so that you see that it can be written with polynomials, then y lies in this set, y lies in this certification here. Okay. And you could write this, you could write this just like r prime prime together with y lies in this classification here. Here I forgot we are. Okay. So actually I think there is one parenthesis missing here. Okay. Good. So that just means for all x there exists an epsilon bigger than 0 such that for all y within epsilon distance, okay, maybe even I should write here epsilon squared, within epsilon distance they lie again in this yeah, okay. And by real quantifier elimination 1817, you apply it several times, of course, right? Look at it again if you forgot about it. Yeah, so you can eliminate these quantifiers if S is a KP semialgebraic class here. Right? You see that this is a zero-ary KP semialgebraic class. Zero-ary, okay, less than or equal semi-algebraic class. Right? Yeah, that's exactly what we wanted to show here, right? But this is just transfer, right? This is the transfer from R to R prime prime. And now, because there are only two zero-ary k less than or equal semi-algebraic classes, the empty class and the whole of curly R, when we are done, right? So because we know that since S is open, we know that the transfer from R to R of S is open, and so we know that R is in there, but when we know also that R prime is in there, right? It's always the same thing. So this line, so if you're acquainted with all these things, then you don't even have to think about it anymore. And if you are not, then I wanted to help you a little bit, but of course you should do it as an exercise. Okay, so what we just did in the last minutes was that that we've seen that transfer preserves openness, right? Okay. And when we have, from this we have seen that in the proof of a finiteness theorem for semialgebraic sets, we can actually reduce to the case where R over K is semialgebraic, right? So, sorry, it's algebraic. R over K is an algebraic field extension. Thus, let now R over K be algebraic, n a non-negative integer, and S a k-semialgebraic subset of R to n. And okay, so and now we show that that it is a finite union of k-basic open sets. Yeah, it suffices to show a green version of a theorem. Here I've actually not even written the other version anymore, right? So we have to show that this is a finite union of k-basic open subsets of R to the n, as seen in the easy part of a proof of 635. For this purpose, it suffices to show that the fattening of S is open, and this follows from a this follows from a difficult part of 635. Okay, now you might say that's not okay, because if you look at the proof of the easy part of 635, I don't see here that okay, so I did not see here that S is a finite union. I saw that S is an possibly infinite union. Okay, and that was because I changed this proof here. I took a proof that was different from the one in the lecture notes, as you see here. The one in the lecture notes actually, and now maybe finally I understand why in the lecture notes I did it in that complicated way. Because this more complicated way shows when already here that S is a finite union. Okay. Yeah, and this more complicated way is as follows. So fattening of S is a union of sets of this form. And now I use that the fattening is closed with respect to constructible topology. I've said this several times already. It's actually a closure of something, right, with respect to a constructible topology. So a fattening of S is quasi-compact with respect to a constructible topology. Now maybe let's look at this finally. So here I refer to 521. I also have used 523 and 5121. So 5121 is this here. So I think what I used here is that closed subsets of quasi-compact topological spaces are again quasi-compact. And yes. And so, and otherwise I use 521. That's the definition of a constructible topology, and also that the real spectrum is compact with respect to a constructible topology, and therefore quasi-compact. And yes. And 5114 is actually just the definition of quasi-compact. So if you have an open cover, it always has a finite subcover. So here we have such an open cover of a fattening of S, and yes, and we have here actually a finite subcover, so we can come back to, what was originally here. So we have here this finite subcover here, and then I just apply that the slimming is an homomorphism of Boolean algebras. So finally I understood, I think, what I wrote at the time. So in fact, by taking this slightly more complicated proof, which uses the quasi-compactness of a real spectrum with respect to constructible topology, I can see here that why the abstract version implies the concrete one, right? Okay. The abstract version of his finiteness theorem implies a concrete one. Okay, the strengthening of, as I said, any true statement implies any true statement, but implies somehow conceptually in a way that's not too hard. If I did not yet know that the finiteness theorem for semialgebraic sets is true, but I knew already that the abstract version is true, and I could derive easily the concrete version from the abstract version. So now the strengthening of 538. So let's remember what was 538. So in chapter 8, R was algebraic over K, right? And okay, and so that's what I write here again. R is algebraic over K, and 538 now was something about the real spectrum. So I have a bijection between the real spectrum of a polynomial ring in n variables over R and the one and the preordered ring AT, where A is a polynomial ring over K, right? And T is generated by the non-negative elements from K. Okay, so I have this canonical bijection, and here what we have in addition is that this is a homeomorphism with respect to both the spectral topology on both sides, as well as with respect to the constructible topology on both sides. So a map is continuous with respect to both topologies that we have already done. That was in a much more general context. That was 527. Let's look at it again. 527. That was this much more general fact with spare maps, right? Induced by ring homomorphisms. Here the ring homomorphism would be the inclusion from K adjoint X into R adjoint X. So it's continuous, and it's bijective by 538. 538. Okay. Right, so here. So continuous and bijective does not yet imply homeomorphism in general, right? Just take any set M with at least two elements, and then equip it once with a discrete topology and once with a trivial topology. So in the trivial topology, you have only two open sets, the empty set and M. In the discrete topology, you have four open sets, all subsets are open. And when take the identity from M with a discrete, let's say M discrete, to M trivial, right? And that's certainly continuous. But the inverse map is, and it's a bijection, but the inverse map is not continuous. The inverse map would go from M trivial to M discrete. Okay. So according to the definition of a homeomorphism, we need to show in both cases a spectral topology on both sides and a constructible topology on both sides. So in both of these cases, we have to show that open sets are mapped to open sets. Images of open sets are open sets. Okay, so well, and this is enough it's enough to show for if you have generating systems of a respective topology, then it's enough to show for the sets, for these generating sets, right? For these generators. Right, and these generators, if you remember the definition of both topologies, in both cases the generators were constructible subsets. But in the case of a constructible topology, these were all the generators we actually used, right? So so it suffices to show that images for the case of a constructible topology, it suffices. So if you want to show that sets open with respect to a constructible topology are mapped to open sets with respect to a constructible topology, it suffices to show that constructible sets are mapped to well, it would be enough to show that they are mapped to unions of constructible sets, but we will actually show that they are mapped to constructible sets even. Okay? So here the image of C under this map is actually constructible. So this, what I highlight here in green, shows in particular that this map is continuous with respect to a constructible topology, right? And what I highlight now in yellow, namely that for all C for all constructible C which are open with respect to a spectral topology, of course, this image is open. That means that this map is continuous with respect to a spectral topology, right? Okay, so yes, so what I show is now that if I have a constructible set, its image is constructible, and in case it is open, its image is also open. Okay, so let's do this. So let C be a constructible subset when its slimming is of course a semialgebraic subset of R to the n, and thus even K semialgebraic by 537, since R over K is algebraic. Yeah, 537. This was a long time ago, but you see here in 5. Here R was algebraic over K, right? Okay, and so if I have a constructible set, if I have such a k-semialgebraic set, I can write it in this way with polynomials whose coefficients are in k. That's just this very general fact, 611. Let's look at it again. Here. I mean, that was actually a reminder. Good. And one can choose VFIs to be 0. Well, that's for the case. Okay, so maybe let's ignore this for a moment. So in order to not get too confused, so for the moment, this is still not relevant here, because I'm concentrating first on the claim that images of constructible set are constructible. So now I fatten this, and I get this, right? And okay, and yes, but with fattening, yes, fattening this, I get this, and so and therefore I get that if I take now the image of C under this map, so this is this, I get that this is, I intersect these things here with A, and so I get here prime cones in the real spectrum of AT, and that the old prime cone satisfied this equation and so on, with inequalities that just because we have phi's and Gij are actually coefficients over k, that gives just exactly the same condition, right? I mean, that just means, okay, so that, for example, means that if I lies in pi intersected minus pi, right? But now if I, since if I lies in A, right, I can also intersect here, I write this in blue, with A, right? And so on and so on and so on. Okay. Okay, and now and now I'm done, because this is yes, this is now, so what did I do? I did the slimming. When I said, okay, because R over K is semialgebraic, the slimming can be written with polynomials over K. And when I did the fattening, and I saw that, yeah, okay, I still have this, can be written with polynomials over K, and now I can do this intersection with A, and I get exactly the same representation here. And this is of course constructible subset of a period during AT. And now for that proves the thing for that proves that images of constructible sets are constructible. And now I wanted to prove also that images of open constructible sets are open. And for this, I use so the claim here that refers to a constructible topology, that's got nothing to do or little to do with subsection. In fact, the main thing is that it's that open sets with respect to a spectral topology are mapped to open sets with respect to a spectral topology, and that uses the finiteness theorem for semialgebraic sets, which is the main topic of this section, right? Why does it use this? Because in that case, so if I have here an open set, it says that I can find such a representation without this equation fi of x equals 0. I could just say with the additional constraint that fi is the zero polynomial, that vfi is our zero polynomials, right? By the finiteness theorem for semialgebraic sets. And then I do exactly the same thing, and here I have again 0 equals 0, so I can forget about this. And then this is of course open. Okay. So if C is open, then this is open because of a choice of fi equals 0. Great. So we are almost done. So in the situation of 635, so one can obviously, so in the situation of 635, so maybe let's look. So that was that R over K is algebraic, right? If and we write A for a polynomial ring over K and T for this pre-order ring generated by the non-negative elements of K. Right, so in this situation, so maybe I write it explicitly here. If R over K is algebraic, and A equals K adjoint X, T is a pre-order generated by the negative elements from K in A. I said one can, now you can, it's not written anymore, but 6112, you can generalize 6112, so maybe let's look at 6112, what it was. It was this thing here, so maybe let's take a copy of that. So R to Vn is equipped with the initial topology with respect to all maps from R to Vn to R, X maps to P of X, where P is just in A. Now that is really easy. That is really easy because, you know, by the definition it's a product topology, so actually you can just take sets R to Vn to R, X maps to Xi, right? And there are special cases of such maps, but these maps are all continuous, of course. Right, so we know already that it's, if you take here all polynomials with coefficients from R, when that is true, and here I say it's true for if I take polynomials with coefficients from K, but actually it's already true if you just take polynomials with coefficients in 0, 1, because these have 0, 1 coefficients, right? These are given by polynomials which have only 0, 1 coefficients. Okay, so that's trivial. So then now one thing which is more subtle is the next one. because now I'm saying the topology on R2Vn is generated by these sets here. Now that looks, I don't know if I was aware of that when I wrote this. So when I wrote this, it might have been that I thought that's now trivial from A. That follows trivially from A. And in fact, here in 6.1.12, it does, right? Because you have here, I mean, what follows trivially from A here in 6.1.12 is, of course, that the topology is generated by the pre-images of open intervals, right? That's quite easy. So, so that it's generated by sets of this form, where A, B are in R, right? So that's quite trivial. And then, you know, since x maps, function x maps to p of x minus a, for example, right? Since that is again given by a polynomial with coefficients over r, right? Just subtract from a constant coefficient with a here. So when in 6.1.12 this follows very, very easily from A. But here you have a problem, right? Because here that might not be given by a polynomial with coefficients over k, right? Because you want to subtract from a constant coefficient a, but a is in R and might not be in k. So here we have actually a problem. I don't think I was aware of this when I wrote it, when I wrote the lecture notes initially. So what are we going to do? Maybe we should first prove the next thing. The next thing is exactly the analog of this, right? So this is exactly the analog of a thing we had already here. Just I'm taking here corresponding prime cone of A. Px is here consists just of all f in A, where f of x is non-negative. So this map is still injective here, 363. Let's look at 363. Here, right? So yes. Yeah, here we had also R over K algebraic, by the way. Okay. Good. So yeah, so maybe let's first look at C. Why is C true? And here I guess I use what we have proven. I mean, here I referred actually to 637. You could do it in different ways, I think, using the results of this section. So you see here that we have this homeomorphism here. And I'm using the non-trivial part of this 637, which is a case of a spectral topologies on both sides. Okay, so let's forget here about the constructible topology. So if I don't say anything, I mean the spectral topology. So let's forget about that, in fact. So the thing is that this is a homeomorphism, right? And maybe let's copy it below. So I will use this. Okay, so you know what I'm saying here is that the topology on R2n is that R2n is actually endowed with the initial topology with respect to this map, right? It's the coarsest topology on R2n, so our topology on R2n is the coarsest one that makes this map continuous, right? So that's what I claim, and I can of course compose with the above homeomorphism. I mean, if I take the inverse map here, the inverse map of this map, right? So it goes then from the real spectrum of so yes, I mean, it's very easy to see that I could, okay, so I did not do this here, but I could have written, and that's real clear, I could have written here also AT, right, instead of real spectrum of A, because all these Px are actually contain, of course, one or negative elements from K, and the topology on the real spectrum of AT is, of course, induced by the real spectrum of A. It's the subspace topology. Yes, so sorry about that. But now if I take the inverse map of this, that goes from the real spectrum of AT to the real spectrum of Rx, right? And it maps and it obviously maps Px to let me just take away the name of it. So it maps this to obviously to this, right? I mean, the map here maps obviously this to this. That's completely trivial. And therefore the inverse map, which goes from the real spectrum of AT to the real spectrum of R adjoint X, maps this to this. Okay. So and now, so in other words, now what I claim now, and since this is a homeomorphism, right? I claim actually that R2, I claim here in 638C, equivalently that R2, the map from R to Vn to this, that maps X to this, is continuous, right? And that's exactly what's written here in 6112C. Good. And then, so I think so that was completely trivial, and that was using 637 and 112C. 112C. And what's still missing is part B, but that's now part B should now follow from C, because the topology on the real spectrum of A, of course, is generated by the sets of a form P in the real spectrum of A, such that f hat of P is positive, where f runs over all elements from A, right? Or P, maybe I should have said, because here I write P, it doesn't matter, of course. So, and from this, from this you see easily that topology on R2n is generated by these sets where P ranges just over polynomials with coefficients from K. So here, in the lecture notes, I have to change something. I have probably to say that this follows from C, and maybe when I change the order or something, follows from C immediately below. Yeah, that I have to correct in the lecture notes, and also in the lecture notes I should probably say something about why I used this kind of complicated argument here. Namely that I used actually because I wanted to say here that when I refer here to the first part of a proof of theorem 633, here in this remark 636, where I want to argue that the abstract version implies the concrete version of the finiteness theorem for semialgebraic sets. I really need this more complicated looking proof here, right? Which uses this argument and which works here with finite unions instead of arbitrary unions. So I don't know exactly what I will do with the lecture notes. I will try to make this more clear in any way. And but I think we are done for today, and thanks for listening. Hope you join us next time when we start a chapter on convex sets in vector spaces. So it's getting much easier now because we start a new topic. Many thanks for listening, and goodbye.